The last objective of section 2.2 is that the student will be able to graph piecewise defined functions. What is a piecewise defined function? Well, you know one that we've seen already, and that is the absolute value function. It's defined in pieces, a left piece and a right piece. On the left, that is where x is less than 0, the rule that holds is negative x, and on the right it's just x. When x is greater than 0, it's just x. And you're like, that thing right there, how can that be right? Because I thought absolute value can't be negative. Well, you're right, because negative x is positive when x is less than 0. This function is defined by different rules for different parts of the domain. You can see the V-shaped graph in your mind. Functions whose definitions involve more than one rule, could be more than two, could be three or more, are called piecewise defined functions. Graphing one of these functions involves graphing each rule over its appropriate portion of the domain. Example: 2 minus 2x is going to be the rule on the left, that is to the left of 2, and x minus 2 will be the rule on the right, that is if x is greater than or equal to 2. It's helpful to imagine, what if you didn't have the ifs? You know, what are the full graphs that we're going to smash together look like? Well, then we would have, say, y1 equals 2 minus 2x, 2 minus 2x, which has a y-intercept at 2, a slope of negative 2, so over 1 down to get an x-intercept at 1, 0. Rise 1, run negative 2, rise 1, run negative 2. That's what happens when you have a slope of 2. Or rise 2, run negative 1. Yeah. Rise negative 2, run negative 1 is the same as run 1, rise negative 2. It's rise over run, so rise negative 2, run 1. Rise negative 2, run 1. Rise negative 2, run 1. So without the if, the graph looks like that. For the bottom rule, it would be a y-intercept of negative 2, a slope of 1, and we would have a graph of like this as we rise 1, run 1, rise 1, run 1, or rise negative 1, run negative 1, rise negative 1, run negative 1, to get a graph like that. Well, now we're going to smash them together into one graph, just like Preston Tucker and Evan Gaddis. One guy on the left, one guy on the right, which together make one complete guy. Here's how the graph looks when you put it together. Now, part of being able to make an accurate graph, piecewise defined, is knowing what to do with the endpoints. Of course, the rule changes at x equals 2. So we have to put our endpoints there and figure out where they're supposed to go in the vertical. At 2, the top rule is going to return a value, a y value, of negative 2, 2 minus 4. And so the top rule is going to have an endpoint at the point 2, negative 2. It is not a part of the graph. Okay, there's 2, negative 2. It's not a part of the graph, so we have to have the open circle there because there's no little equal sign underneath the inequality symbol. as there is on this other rule. There, evaluating the bottom rule for x equals 2, we have 2 minus 2, which is 0, and so that'll be the y value when x is 2 for the bottom rule, and so now we do have that endpoint. Notice that the point 2, 0 is included on the graph, but the point 2, negative 2 is not. We couldn't have them both, because if we did, then this graph would fail the vertical line test and not even be the graph of a function. On a TI-84 CE graphing calculator, we would do our inputting like this. You need parentheses. Somehow that opening parenthesis on the first one didn't get there, but that's how it's supposed to look. Parentheses around the two rules, and then parentheses around the if parts. Where do you get the inequality symbols to go into the y equals menu? Okay, so you're sitting in the y equals menu, and you have to get to this menu, which is the test menu, and to get there, it's second, which in a lot of these calculators is a yellow button. Second, math. Second, math. And then 5 is going to give you the less than symbol that we used in the top rule, which is the rule for y1. And second, math 4 would be what we'd use to get the greater than or equal to symbol that we need in y2. The result ends up looking like that. Never mind the colors on the x-axis, and never mind the fact that the resolution is still not such that we could have the open circle and the closed circle where they are supposed to be. This graph does confirm our work.